की तबीयत ठीक नहीं है, तो आगे की क्लास, आज की क्लास लास्ट क्लास है। इस थ्योरम से और कुछ रिजल्ट्स बेसिक बच गए थे जॉर्डन फॉर्म, को आज हम कवर करेंगे। ये थ्योरम कल सर लास्ट में कर रहे थे। इसमें ये था कि तो कुछ पार्ट इसमें मिस, थ्योरम बार रिकॉल कर देता हूँ। ये थ्योरम थी px polynomial means minimal polynomial of a linear transformation T comes to A of V is qx की power L1, q2 की x power L2 and qk x power Lk, and each qix are irreducible over the field F. Then we have defined V1, V2 and Vj of this form for all j equals between 1 to k. So we have to prove these things. Means V1 is the element of vectors of V such that V and Q1t raised for L1 is 0. Similarly, V2 is V vectors, all the vectors in V, vector space V, such that V Q2 T L raised for L2 equals to 0 and so on. So we have the following results. So sir है proved point 1, point 2 and point 3. So today we will see the proof of 4 and 5 and some other theorems. So yeah, up to here sir has done. So yeah, here point 4. So V equals to direct sum of V1, V2 and up to Vk, and let us H1x equals to Q2. Means we have removed from here Q1 part and define H2, that is we remove H2 part. Means Q2 polynomial factor, irreducible factors of Q2 we have removed from the minimal polynomial, and we define H1x and H2x. So the GCD of H1 and H2x is Q3 to Qk, means it does not contain Q1 and it does not contain Q2. So similarly we can see if we define H1, H2, Hk, means H1 it does not have the factor of Q1, H2 it does not have the factor of Q2, and Hk it does not have the factor of Qk. So in the similar way we get the GCD of all these H1, H2 and Hk equals to 1. So this implies that H1, H2 and Hk are relatively prime. Okay, so by basic theorem of number theory and field theory, that if 2 means just like if two H1 and H2 are relatively prime, then we get two polynomial A and B such that A1 and A2, let's say, then A1H plus A2H equals to 1. So here we get similar way polynomials A1, A2 and AK in the polynomial over the field F such that A1H1, A2H2, AK-HK. This will equal to 1. Now we operate T in place of X. Then 1 become identity map and A1T, H1T and AKT, HKT. Now for a vector V in vector space capital V. So V equals to VIV, means identity operator we apply. So here we apply small v over this whole operator, polynomial operator we can say. So V, A1T, H1T and up to AKT, HKT. So we apply V, A1T, VK, AKT and HT. Now this will belongs to V, H1T. V means capital V means vector space, means is small v belongs to vector space, then A of T, V belongs to capital V, while because it is a linear operator, means t is a function from v to v over the field f. So this will be v1 h1t plus b hkt, and by the definition of v1, v2 and vk as we have defined above, this is the subset, means h1t vectors will in which are in h1t or belongs to v1, and for the vectors which are in hkt belongs to vk. So this whole term is subset of v1 plus v2 plus vk. Now for v hit qit let for li, so we get this v hit qit let for l, this equals to v pt 0. This implies v hit means this vector. If we assume this as a small v as we defined above, then we operate this vector v, that is v hit, then qit let for lit, then it becomes 0. This means this vector belongs to v1, and is if we take here capital V is vector space of all those vectors which are, means all the vectors in the vector space capital V. So this becomes subset. If you take one element, then it belongs to this Vi, and if you take whole vector space, then it is the subset of Vi. Hence each V belongs to V can be written as, say, sum of this subspaces, and where Vi belongs to Vi for all I, means V1 belongs to V, V2 belongs to V2, and Vk belongs to V. So to show direct sum, we show that they are disjoint, means these sum, the sum that we have written is unique. So suppose V equal to U1 plus U2 plus UK, Ui belongs to Vi, means we have assumed that V can be written as this way and V can be written as this way also. Then we have so that V1 equals to U1 and V2 equal to U2, and so on, Vk equals to Uk. So this implies that this whole V can be written as unique, linear combination of or sum of elements of Vi. Okay, so here just subtract these two, this V and minus this V. So we get 0, V1 minus U1, V2 minus U2, and so on. Now we want to show that V1 minus U1 equals to 0. If it becomes 0, this implies V1 equals to U1, and which implies that it is become unique representation of V as a sum of vectors in Vi. So on contrary, we assume that V1 minus U1 is not equal to 0. If this one is non-zero, but then 0 equals to be operating H1t in this on this vector. So 0, we operate H1t, becomes 0 itself. Then V1 minus U1 H1t and U2 V2 minus U2 H1t, and so on. So all these H1t has the factor. What is the H1t? H1t does not have the factor of only Q1, and all other it has factors. And these V1 and U1 belongs to VIs, capital VIs, V1, V2. So for let's see for this one, V2 minus U2 belongs to V2, and in what are the elements are in V2? All those elements which are 0 when we operate Q2x, Q2t raised to power L2, and H1 has one factor, Q2 raised to power L2. Why? Because H1 only does not have factor of Q1 raised to power L1. So this will become 0, and H1 also have factor of Q3, Q4, and all other. So all the other terms except H1t, it becomes 0. Now this implies Vj Hit equal to 0 for all I not equal to G. Okay, because we have shown that if I told here, that is written here, for I not equal to J, Qj x raised for Lj divide Hi. So Hi is the multiple of Qj and with some Rjs. So when we apply Vj on Hit, it becomes 0. So finally we have V1 minus U1 H1t equals to 0. Also V1 minus U1 H1 Q1 rate for T L1 equals to 0. We have this one because this one belongs to V1. We have take small v1 minus small u1, both are in u1, so their difference will be in v1. And by definition of either subspace or vector space that we have formed V1 is by this condition. So further H1x and this are relatively prime. So there exists a polynomial again B1 B2 in fx such that 1 equals to H1x plus B1x plus B2x plus Q1L raised power L1x. And when we operate T, so we get I equals to H1T, B1T plus B22 plus Q1L1T. Now we operate this vector over this operator. So this is an identity, we get this same. And for this one, we get this one. Now we know H1T equals to this of this equal to 0 and Q1 of this vector V1 minus U1 is 0. So what we get in right side, just operate H1T, take B1T after that, and this one and B2 after that. So we get 0 plus 0. So what we get, V1 minus U1 equals to 0. This implies V1 equals to U1. So we can similarly do for other, means for V2 minus U2, we take H2 and Q2 in the similar way. And so we get Vi equals to Ui for all i's. So this implies that V can be written as the linear sum of or elements of sum of elements of Vi's and in unique way. So this implies that this is direct sum, means V is the direct sum of Vi's. So any doubt anyone here? Any doubt? Okay, so if there is no doubt, so let's proceed to fifth point. So 1. Pix, the minimal polynomial of Ti on Vi equals to Qi x raised power Li. We have to show this one. So what we have to show that this operator Ti that is restricted on Vi is satisfied by this polynomial, and this one is the such polynomial is of least degree. Okay. So firstly we can see Qit raised power Li equals to 0. This implies Pix divided Qix raised power Li, means if we are assuming that Pi be the minimal polynomial, then we have to show that Pi must be equal to Qix raised power Li. So we can see easily Qit raised power Li. If we operate Vi for this one, then it will become 0. So this means Qit raised power Li is 0 operator on Vi. Means if we restrict Ti on Vi, then it becomes 0 operator. So by the property of minimal polynomial, the minimal polynomial Pix divides the every polynomial which annihilates the operator T. So here operator T is Ti and minimal polynomial is Pi, and Qix raised power Li is satisfying the operator T. So this implies that Pi divides the polynomial. Minimal polynomial that we assume Pix is minimal polynomial, so it must divide the polynomial Qix raised power Li. And now Px is minimal polynomial, we have assumed that. Okay, Px we are assuming that minimal polynomial of T over F. So Pi is the minimal polynomial of Ti and Px is the minimal polynomial of T over F. That is LCM of Pi's. That is LCM of Qi raised power x raised power mi. So this implies Q1x raised power m1, Q2 raised power m2, and so on up to k raised power mkx. So, and we have shown that these are irreducible, means they are relatively prime. Means Q1x raised power L1 and Q2 raised power L2 and Qk raised power Lk. Each Q1, Q2, and Qk are irreducible. So this means they are relatively prime. So we get the Px equals to product of all these things. So this implies Px is the minimal polynomial of T. So this Px divides Q1 raised power x raised power m1, Q2 raised power m2, Qk raised power mkx, where m1s are mi's are greater than li's. Okay, so this implies li equals to mi. Why? Because we have proved here this the minimal polynomial of Px is of this form, and we know that this Px is of the form this. So this implies and minimal polynomial is unique. So this implies L1 equals to M1, L2 equal to M2, and so on. But Pix equals to Qix raised to power Li. Is it clear or not? How this will imply this one? Any doubt? Anything? Okay, so if there is no doubt, so it's okay. We have proved that Li equals to Mi. Let me just clear once more this part, how this one is happening. If Li equal to Mi, means the minimal polynomials are Q1x raised to the power L1x and Q2 L2x, and this is the product of the minimal polynomials of the restricted operators. And we have proved that any other operator that is means Li or Mi. So this implies Pix must be equal to Qix with power Lix, because we have assumed that this Px is the product of Pix. We have done already results on this. So from there we can get, and we have proved that this Px is the product of this one, and each Li is equal to Mi for any other polynomial. So we get Pix equals to Qix with power Lix. So any doubt in above proof? Anyone? If anyone has any doubt, please ask. Okay. We have a corollary for this. If all the distinct characteristic roots lambda 1, lambda 2, lambda k of t belongs to A of V, means t is an operator from V to V, are in F. Means distinct characteristic roots of lambda 1, lambda 2, lambda k are in F. Then V equals to V1 plus V2 plus Vk, means V is the direct sum of V1 plus V2 plus Vk, and where Vi's are, V belongs to V, such that V t minus lambda I raised to the power Li equals to 0. So it had followed from the above directly. And where Ti is the restricted linear transformation on Vi has only one characteristic root, lambda I. Means if we restrict Ti to Vi, then we have only one characteristic root, that is lambda I. Maybe multiplicity of lambda I different, but the distinct root must be only one, that is lambda I. So let's have a proof. Since all the characteristics roots of T lies in F, so all the roots of minimal polynomial Px of T lie in F, because minimal polynomial has all the roots that are of characteristic polynomials root with different multiplicities if possible. So lambda 1, lambda 2 and lambda k. So Px equals to x minus lambda 1 raised to power L1, x minus lambda 2 raised to power L2, and x minus lambda k raised to power Lk. When lambda 1, lambda 2, lambda k are in field F, are all distinct, means these roots are distinct. So means the minimal polynomial has its roots with different multiplicity. We don't know L1, L2 and Lk, what are these, but we can use above theorem that we have proved properties, above 5 properties. These are different. So Px must have all this as a root. And by above theorem, what we have, V equal to V1 plus V2 plus Vk, direct sum, where Vi's are this, means V Qit raised to the power Li equals to 0. And Qit means, what is Qit here? This one, Qit. Qit, if you, this one is Q1x actually, so if you operate T, we get T minus lambda I raised to the power Li equals to 0. And the minimal polynomial of Ti's are Pix, that is Qi raised to the power Lix, that is we have shown or seen above theorem. So Ti has only the characteristic root lambda I. Why? Because minimal polynomial is this one, and this has only lambda I root. So it has only with multiplicity Li. Okay, any doubt or anything here? Okay. This, let me see once. Okay, these are some examples. I think it's not arranged in proper way. Jordan form. Now we have to read Jordan form, and let us, yeah, from here that example is not arranged in correct manner. The basic Jordan blocks. So what is Jordan block means? We are trying to find a representation of linear transformation in terms of matrix. Means if can be done something up to unique, or we can characterize some transformation. We know that linear transformation can be characterized by matrices, and if the matrices are, if two matrices are, two linear transformations are similar, then what can be said about Jordan means what is the matrix form? Is there any general form for them? If linear transformation is diagnosable, then what can be the matrix form? Means what is the general form of a linear transformation having some specific properties? Can we have something like that? So for that we are introducing basic Jordan blocks, means known as that is Jordan form, means a Jordan block form of matrix. So for any linear transformation we can have Jordan block form, and they are in general form and they are unique in some sense. If we have two, let's example we will do later in a theorem that states that if we have two linear transformations which are similar, then their Jordan blocks are same. So this one is the importance, and if we have diagnosable linear transformation, then it has a special type of Jordan block form. So we can study a lot about the properties of matrix by using Jordan block. So to form Jordan block for Jordan matrix for a given linear transformation, first we have to know basic Jordan block. What is basic Jordan blocks? Because the combination of basic Jordan blocks we form the Jordan matrix for a given linear transformation. So a square matrix is said to be basic Jordan block belonging to lambda if it is of the form this. Means we are getting a basic Jordan block for a fixed, means if a linear transform has lambda 1, lambda 2 or any number of characteristic value, so we get basic Jordan block for each one lambda eigen values. So this one is this, we have on diagonal we have lambda means eigenvalue with respect to which we are finding the basic Jordan block, that is n cross n, and above all that is 1, means just above diagonal elements row, means what we can say upper diagonal, just above the diagonal element we have 1 1 1. So that is lambda in plus mn such that this property, means if we have other, this means this one is diagonal element, so here we get 1 1 1 up to here 1, and this diagonal element has lambda, then this matrix is called basic Jordan block with respect to the eigenvalue lambda. Now there is a theorem, let's let a T belongs to a linear operator on V have all its characteristic roots in F if lambda 2 1 lambda 2 lambda k are all of its distinct characteristic roots. Then there exists a basis for V in which the matrix of T is of the form this. Means if we have a linear transformation on over V over the field F, and if it has lambda 1 lambda 2 lambda k distinct eigen values, then we get a basis of V for which the matrix representation of T has this form, where J1 is basic Jordan block for the eigenvalue Z lambda 1, J2 is the basic Jordan block for eigenvalue lambda 2, and these are of the form, means J1 is have the form of, if we say J1 here, so on diagonal it has lambda 1 lambda 1 lambda 1, and above the diagonal elements are 1 1 1 and all others are 0. So this one is the basic Jordan block for J1, for J2 and up to Jk. So if dimension of V is n, then we have the matrix J n cross n and J1 J2 and Jk. And after, so we are saying here just only existence of such matrix, and later on we will see how to find J1 J2, means what is the order of J1 matrix. We get J1 is a square matrix with this property, but what is the order of J1 we will see it later. Okay, is of the form where Ji is this one, basic Jordan blocks with I1, I2, IR, where each B1, BI1, BI2 and BIRI is a basic Jordan block belonging to lambda I. Means Ji is this and this one is basic Jordan block for lambda 1 and Ji is the matrix which is means a collection, or you can say in some manner it has basic Jordan blocks for lambda I. So let's prove case 1 where T belongs to this has only characteristic root lambda. So we have V minus lambda, T minus lambda I equals to 0 for some V not equal to V, means by the definition of eigenvalue and characteristic root. So lambda belongs to F. This implies lambda is a root of minimal polynomial. Since this is the only root, we are considering the case if has only one root. So we get minimal polynomial of T to be of the form x minus lambda raised to power S. S means S is less than or equal to n. If the dimension of vector space V is n, then x minus lambda raised to power S is the minimal polynomial of T. Hence, we operate T on T minus lambda I over V, then we get 0 by minimal property of minimal polynomial for all V in V, सभी V के लिए. So T minus lambda I raised for S equal to 0. This implies T minus lambda I is nilpotent of nilpotency index S. Means the operator T minus lambda I is a nilpotent matrix, nilpotent operator. It becomes with nilpotency index S, and what is S? S is the power of x minus lambda in minimal polynomial form. So there exists a basis for V in which the matrix T minus lambda is of the form this. We have studied this one already, that how it is looks like for a nilpotent operator. So for that we get a basis for which the matrix representation are Mn1, Mn2 and Mnr, that is R cross R matrix or n cross n. For if we taking it means that we get what is the value of this one, where S is equals to n1 greater than or equal to n2 greater than or equal to nr, and n1 plus n2 is the sum of is equals to n. Means the whole matrix, because it has only lambda eigenvalue, and we get T minus lambda I is nilpotent operator, so its matrix form has this one, and the dimension of this small matrix block matrices are n1, n2 and nr, and the sum of these must be equal to n, and S is the nilpotency index. So this one is the n1 can be maximum, means if we take say about n1, n2, nr, what can be the maximum value of the small block matrices? So it cannot exceed the nilpotency of this, and it can be less than that. So maximum possible order of these blocks are the index of nilpotency. Hence the matrix of the T is of the form this one, lambda in, this one T minus lambda I, that is lambda in plus this matrix. So this implies lambda in plus mn, and this will get, this means what we get, mn means this diagonal element we get lambda, means in means a matrix. You can visualize here that these are the, we get on this diagonal element lambda, and just above the lambda we get 1 1 by you can, if you remember that what we have discussed about nilpotent matrix representation. So these implies that these are the basic Jordan blocks that we have defined above, and we say this one is J1 or J basically because it has only one eigen value, and Bi's are lambda ini plus mni. So this one is the first case when it has only one eigenvalue. So any doubt or anything? No. Okay. So for case 2, so minimal polynomial of T is of the form this one. Now it has k distinct eigenvalues. This multiplicity is L1, L2 and Lk in minimal polynomial. So, and all these lambdas belongs to F. This one is compulsory condition. Please don't forget this one. All that thing we are talking about, the eigenvalues must be in the field where we are discussing. Otherwise, we can't get the a matrix in that field. So by above theorem that we have discussed earlier, V can be written as the direct sum of Vk, where Vi's are this one, the vectors which are annihilated by T minus lambda I get for Li. So, and this Vi is T invariant, and minimal polynomial for Ti's are Pix, yes. Here Ti's are the restriction of T over Vi for all I 1 to k. Then each Ti minus lambda I rated for I is nilpotent. As why this one is nilpotent? Because T minus lambda I, here you can put I, it is missing here. Rated power Li equals to 0. In fact, Li will become nilpotency index of T minus lambda I, as this one is the minimal polynomial, x minus lambda I rated power Li. So by definition of nilpotency, we can say that Li is the nilpotency index of T minus lambda I for Ti. So by case 1 means now we are forming one for lambda I, we are getting a Jordan block which collect the basic Jordan blocks, which has the combination or some combination of basic blocks. So by case 1, if we so Ti has, if we choose, there is a basis Bi for Ti, because Ti has only one eigenvalue, that is lambda I. Okay, and we have proved that Ti has only eigenvalue, that is lambda I. That is, means Ti is having only one eigenvalue, and we can use case 1. So from case 1, we can get a basis Bi in which the matrix of Ti is of the form this one. Ji is the form of this one, that is lambda I plus mn I, and taking ordered basis B equals to B1, B2, Bk. Now we use the matrix form of the, if the our vector space is direct sum of given some V1, V2, Vk vector spaces. So what is the matrix of this one? And for each Vi, we get Ji of the form this, that is Jordan form of the blocks. So we get a matrix T with respect to B of the desired form. Desired form means if B1, for B1 we get this block matrix. So for B1 we get J1, and for B2 you get J2, and so on, and where Ji's are of the form this one. And the order of this matrix must be n cross n, and the order of Ji's is the Li cross Li. Means you can say directly the dimension of Vi. Ji, order of Ji is the direction of Vi, and the basic block, that is Bi is 1 Bi 2 Bi r, it has, what is the order of this? So these basic blocks has possibly maximum order can be only the index of nilpotency, and which is only first one maybe, and all other are less than or equal to that. So this one is the basic idea about how we form a Jordan form. So first we see that we form a Jordan block for a given eigenvalue. A Jordan block has basic Jordan blocks, and how the basic Jordan blocks are formed? They are of the form this one, means a lambda and the at the diagonals, and just above there is 1 1 1. If it is 1 cross 1, then it has only 1 and all other things. If it has, means basic has 2 cross 2 matrix, then it is a lambda 1, means lambda lambda, and 1 and 0. This one is the basic Jordan block for this one, and Ji is of the combination of this one, means you can say it has, you have here lambda 1 lambda 0, here second one you can have only lambda, third one has only lambda. So this one is Jordan block for lambda eigenvalue, and all others are big. And similarly we get for Jordan blocks for other eigenvalues and combine them all, and we get the required form of the matrix, which is called Jordan block. And we have proved here that for a Jordan block there must be exist a basis in which we get its Jordan form. If we take that order basis, we get Jordan form of the matrix. Here is a corollary. Two linear transformation AV which have all the linear characteristic roots in F. This one is necessary condition, because if the eigenvalues are in not F, then we cannot get a matrix for means over that field. So this one is the necessary condition first off. If you talking about Jordan form, diagnosability, anything like this in which eigenvalue involved, then eigenvalue or characteristic root must be in the given field. Otherwise, it is not satisfy that property. For example, if you can take, you have already studied, just let me recall the importance. If you take 0, a matrix of from this 0, -1, 1, 0. So it is this matrix is diagnosable over R field, if we say, because the matrix is real, so we can talk about diagnosability over R. So you can say that its eigenvalues are in complex, not real value. So this matrix is not diagnosable over R, but it is diagnosable over C. So this is the importance of field. So whenever you are mentioning or reading these things matrix form R, so you must clear about that the characteristic roots are in that field or not. Otherwise, some properties may change. Means just like the above example, it is diagnosable or not diagnosable. So okay, here so in this corollary we are saying that if two linear transformations are similar, if and only if they can be brought to the same Jordan form. Means if two linear transformations are similar, then we get a same Jordan form. Means here it is written that they can be brought to. Means if they are not in the same form, we can use the property of Jordan form and we can get same Jordan form. So if you have given that if two linear transformations has been given to show that or to check whether they are similar or not. So one definition is that there exists a invertible operator S such that T1 is equal to S, T2 S inverse. That's okay. But from Jordan point of view, you can see by forming their Jordan forms, and so that both linear transformation have same Jordan form. Means for T1 there exists a basis B1, for T2 there exists a basis B2, such that the matrix form of T1 with respect to B1 and T2 with respect to B2, they are equal and they are from Jordan form. For matrix over F having all their characteristic root in F. So this one is important that I am already saying again and again. The eigenvalues must be in the given field, otherwise we can't proceed further. And one another corollary is that two n cross n matrices are similar if and only each is similar to the same Jordan form. Again the same thing, means we are saying that any n cross n matrices, first we talk about linear operators, and for the matrices we can get same thing result, because we know matrices implies linear transformation and linear transformation implies matrices. We can represent a linear operator in the form of matrices, n cross n matrices. So the same thing is applied if and only if two given matrices have same Jordan form. Means we can find Jordan form of linear transformation and a given matrix also. So these are the equivalent conditions for in terms of linear transformation and in terms of matrices. So any two linear transformation or any two matrices are similar if and only if they have same Jordan form. And let me see, what is this one? Okay, this one is the remark, let me see. So let A belong to n cross n matrix over the field F, and let K be the splitting field of minimal polynomial for A over F. What does it mean? It means if eigenvalues of A are not in F and we are taking the eigenvalues in K by definition of splitting field. So there exists an invertible matrix C belongs to K and F. We are saying such that C A inverse C is in Jordan form. The simple thing is that we are not going to extend our field. Why? Because if eigenvalues are not in the given field, then we cannot form Jordan form. So for that we are taking splitting field and then performing the same thing. And in the same result like this, and over K, the splitting field of the minimal polynomial of A means over K, the minor polynomial of A have all the roots, means eigenvalues of A are in K. Then the matrix, there is a matrix, this one of this Jordan form, where each Ji correspond to different roots of lambda I of A, means characteristic roots of A, and multiplicities of lambda I as characteristic root of A to be defined as Ni, means the sorry, means the multiplicities of the lambda will define the order, have some order, means order of this one defined Z1, J1, J2 will define by the multiplicity of eigenvalues, where Ni is the order of Ji. So the sum of multiplicities must be n, because n cross n matrix has at most n, or if we can say, if we are talking about splitting field, then it has exactly n eigenvalue. So multiplicities of all eigenvalues must be equal to n. So these are some examples. Find the Jordan form of the linear transformation given by this. So A is a matrix. So with respect to this, you have to find the linear transformation and then find the Jordan form. So let me just show. You can find up to here. This is the linear transform you get. So you first find the eigenvalues of this. So after calculating, you will get the eigenvalues are this one or the eigenvalue. Now you can easily verify that this one is the minimal polynomial. So by the theorem that we have earlier done, we can write V equal to V1 plus V2, because it has two distinct eigenvalues only. So V1 is this and V2 is this. Here is power 1, here is power 2. So we just find what is the V1 exactly, and here we get what is, where it is given. Yeah, this one, we get the V2. So we have separately find the vector spaces using the properties, what is V1 and what is V2. So V1, V2 are t invariant subspaces of V. So for V1, this belongs to this V of t minus I equal to 0. So, and it's had been W belongs to V2. Then we have square, with square is equal to 0. So V equal to x1 plus x2, x1, x2, x3, if we assume this one is alpha times this, beta times this, and gamma times this. You can use above given linear transformation, and V belongs to this property, this one. So by using this one, so all this calculation we will get finally what we get. We get the value of alpha 1 is this, beta 1 is this, gamma 1 is this, and after putting the values of alpha, beta, gamma, we get these are the relations. These are calculation. I will send the PDF file so you can see the examples on your own. These are just calculations followed directly from the theorem that we have done already. So the sum is direct sum. If this one become, means intersection must be phi. Means what does it mean by phi? Means it has 0 only eigen intersection, not phi. So what is the, just recall for 1 second, what is the meaning of direct sum? Means if V equals to V1 direct sum V2, means each elements of V can be written as the linear combination of or sum of elements of V1 and V2 that we have shown here. And for direct sum, means it is written as unique, or equivalently we can say the intersection of V1 and V2 are only 0. So for that we have taken, if element, let's say, belongs to intersection, so it has can be written as the linear combination of V1 element, and this belongs to V2 also. And V1 is the span of 1, 1, 1 as we have seen above, and V2 is the span of -1, 0, 1 and 2, -1, 1. And we assume that this element V belongs to both, means V1 can be written as linear combination of this one, and V2 can be written as linear combination, and both belongs to both are equal, and both belongs to V1, V2. So this implies these must be equal, and from there, after getting calculation, we get this one, beta and R is 0. So this implies V1 intersection V2 is 0. This means this one is direct sum. So first we have shown here, this calculation shows that any vector v belongs to v is a linear combination of v1 and v2, and then we say their intersection is 0, so this implies this one is direct sum. I have done the calculation, I have skipped the calculation part, so just I am telling you the points what you have to show. First we have shown the linear sum of linear any vector in v1, sum of v2 and v2, v1, and then their intersection is 0, this implies direct sum. Now we have to check restriction match, that is T1 and T2 over V1 and V2. So you can find this one. So you can get this basis. We can take this one is basis as a basis because V1, V2 has one element and V2 has two elements as basis. So we take order basis, that is union of V1 union V2. We can take basis of capital V. So from there you get T1, T2 and minimal polynomial of then again T2 is this one by above theorem, and T1 is that the similar as only T minus lambda I means x minus lambda. T1, it has been proved that here the minimal polynomial of T2 and T1 proved means they are verified. We can get from the theorem, but here it is verified that if any element V belongs to V2, then if we operate this operator, then it becomes 0, and there is no other operator with degree less than will satisfy these vectors all. So that means theorem is verified. Now B1 is this, B2 is this. So we just taking that this matrix form of T1B, which is of the form that is 1 cross 1, and T2 is the matrix of this form. So we can put this one. So we get matrix T of this form. Now is it of Jordan form? Not. Why? Because this one is a block for eigenvalue -1. But it what is the form of Jordan form? This is the form of that this diagonal element has eigenvalues, that is -1, -1, and this has 1 and this has 0 because it is 2 cross 2 block, this matrix block. So it is not in the Jordan form. So for Jordan form, these are the calculations has been done. So I will send this PDF, so don't worry to just get the calculations. T2 we have find, T2 of B2 is this one. So we have taken B1, B2 as a basis, W1, W2 like this one. So then we get this one, T of B. Means we get a basis B1, B2 of this form, and which implies this one. So this one is Jordan form because it has eigenvalue as the diagonal and above 1, and all this one are 0. So this one is Jordan form. And this one is the basic, means Jordan block for eigenvalue lambda equal to 1. This one is the block for lambda equal to -1. So this is on the form, and I will send the PDF for calculation your reference for this part. So yes, so any doubt or anything you can ask here. I have skipped the calculation part because it's easy. You can verify yourself. Not that much tough. So yes, any doubt or anything? And also note that the syllabus for the major exams will be from the first lecture to today's lecture, means from vector space basic definitions to Jordan form of a matrix or a linear transformation. So syllabus for major exam will be up to here. And some students are saying for online or offline exams. So as we have not received any mail from Dean or anywhere that for online exam for the students who are has already on board in hostels. So please confirm at your point if there is any mail or any notice has been issued by competent authority that we can take exam for online or offline. Otherwise, that we have received an email earlier that is for onboard students, the exam will be offline, and for the students who are at their homes, for them it will be online exams. And you can further go to Dean or anywhere, means you can ask for them to give you for online exam or offline exam. If you have any information regarding notice or mail received from Dean or anywhere, so please let us know so we can arrange exams accordingly. And exam is on 21st, and I think 9 to 12 time. So please verify once, and otherwise it's 21st November and 9 to 12 exam timing is. So if anyone has any doubt or anything.
Sir, exam will be for 3 hours.
No, it's timing that 3 hours. We can take exam for 2 hours or 2.5 hours. Means the institute had allotted the time. We have to conduct exam within that period. Otherwise, you may have means coincidence means you have two exams maybe coincide. So they have divided 3 hour slot. So we have to perform all the exam within 3 hours. So maybe its exam mostly will be 2 hours or 2.5 an hour maximum. Yes. Anything else regarding syllabus or anything?
Sir, do keep a little more time for the scanning this time
Yeah,
in the major.
obviously 50 marks question, you have already getting 15 minutes earlier, I think 15 or 10 minutes for scanning. So this time at least you get more than 20 minutes for scanning. So don't worry, because if it's 50 marks, the question paper may be a little bit large, so you will get sufficient time for scanning. There is no doubt. And anything else regarding syllabus or anything? So okay, if there is no other query, so
Sir, is there a marks distribution for parts of the major? That means before minor one and after minor two is there any marks distribution like that?
it's not exactly any marks distribution, but most of the marks will come from after minor one, including quiz and after quiz. Before minor one, there is only one or two question, or maybe it has less percentage in question paper. More question come from after minor one, including quiz, and after that we have studied or discussed. Not any exact, but yeah, it has means if you can, I think 15 marks come from minor one, another 35 must we come from after minor one syllabus.
Sir, for offline exam, are you allowed to take laptops to classrooms?
For what?
For offline exams, are we allowed to take laptops to classrooms and write exam?
Mm, no, I think for offline exam we have give you like earlier we give you a paper and question paper and answer sheet both. You have to write and you have to submit by hand. I will inform, but I think this will be happen. But I will ask to professor regarding this.
Some course instructors are doing like that also, sir. They're allowing laptops.
Maybe they are taking open book exam, something like that, or what? I don't have any information regarding that.
I mean, like for online only, offline students also are allowed laptops. That's what they said.
Means maybe they want that everyone upload their answer sheet over in Gradescope, so for checking or for collecting the marks of all students will be easier. Otherwise we have to enter your marks over academic portal by hand, na? If it is online, then it's good for us that we can directly upload all the, and we get over Gradescope, we get on one click we can download all your grades together. So for that matter maybe. So I will discuss to professor for that. If it is be given you question paper and answer it both, or only question paper and answer it, and how you have to submit your answer means on Gradescope or by hand. So I will discuss and I will inform accordingly. And exam is 21, so I will 2 days 10. Na? So I will inform you within 2 and 3 days. Don't worry about that. Anything else? Okay, please now we can in now. Okay, thank you all.